My most impactful project was a multi-quarter project of crossing or merging vehicle handling design, implementation, and validation during my first software engineering role at Motional, a robotaxi company. Working in the planning semantic reasoning team, I analyzed the on-road semantics to provide multiple unobstructed paths to be fed into the model predictive controller to optimize the eagle's trajectories. The objective was to ensure no collision while minimizing discomfort and maximizing efficiency. The unobstructed paths were constructed from the lane graph and the predicted trajectory of the nearby agents. Due to a recent change in the neural network's architecture, the model generated multiple predicted trajectories for each agent rather than single, where the top K trajectories were filtered through scoring. Integrating the multiple predicted trajectories introduced a K-fold latency and vehicle takeover due to hard brake. My first task was to optimize and improve the lane association algorithm. Initially, the lane association computed per waypoint led to inconsistent or missing associations due to ambiguous projections onto lane baselines. These errors caused the Eagle vehicle to hard brake due to false positive lane associations, falsely indicating obstructions. Thus, a linear increase in the number of trajectories caused a linear increase in latency and false positive rate. To ensure consistent lane graph nodes in the trajectory lane associations, I redesigned the algorithm to propagate lane associations nodes bidirectionally with the Viterbi algorithm by modeling the waypoints as hidden Markov model and minimizing a quadratic cost function based on the waypoint's pose and projected state. This approach ensured that all the hard brakes observed causing fatal vehicle takeovers were handled by resimulating over the logs. I further validated the algorithm through additional synthetic scenarios in the test suite, fine-tuning the ego to the desired behavior. With the improved lane association, the next step was to adjust the ego decision tree to account for the added predicted trajectories, making informed decisions not solely based on the most likely trajectory, but also on the other modes of trajectory to effectively represent the agent's predicted trajectory distribution. One of the most critical problems with using only the most likely was the unstable trajectory likelihood score, which often caused similar values for the top two trajectories, causing flickering of the most probable trajectory over consecutive time steps. Instead of naively incorporating all top K trajectories, which would engender intersection clutter, we projected trajectories onto the lane graph, adjusting dilation based on uncertainty. This method provided sufficient initial coverage of the agent's trajectory distribution. The next step was to employ it to enable a safer and interaction-aware unprotected right turn decision algorithm. The observed problem was during an unprotected right turn in the demo route. The oncoming vehicle initially approached slowly, signaling a yielding intention to the Eagle vehicle, creeping into the intersection, but in turn decided to proceed, causing the Eagle to hard brake and block the intersection. To address the problem, a cross-team effort was made for the yield likelihood learned signal of the oncoming traffic. By fusing yield likelihood scores with trajectory projections, I added rule-based checks to the ML output, enabling the Eagle to proceed cautiously if the oncoming vehicle intended to yield. Upon its change of intention, the Eagle would yield dynamically by the stop line until the intersection was clear. This change handled all the problematic resimulations of the logs, serving as a solution to the fatal demo route issue. This project exemplified the intersection of analytical precision and creativity in approaching open-ended problems. To devise and optimize algorithms to address unsolved issues robustly, I learned to balance probabilistic models with deterministic safeguards, a framework applicable in decision-making in noisy and sparse financial market. My fascination lies in integrating various modules such as intent likelihood and trajectory distribution projections into systems that make high-stakes decisions. At NYU Courant, I aim to apply the same analytical discipline to delve deeper into financial engineering to tackle complex problems at the forefront of the industry. Thank you.